Okay, this is going to be our second video in our DC circuits series. In this video we're going to be talking about Kirchhoff's rules. So this is going to be section 26.2 from the textbook. And we'll get right into it here. We're going to talk about pretty much everything they talk about in the text. We have a couple of extra examples that I won't go into here, but if you guys are having any issues with any of the concepts, I would encourage you to take a look at those examples, and then obviously, like usual, we'll do as many examples from the text as you need to get a good handle on the topic. Okay, so Kirchhoff's rules. So we start off by thinking about, well, how do we handle networks that are more complicated than the ones that we've looked at already? So we're going to run into a number of systems where we have resistors set up in networks where it's not so simple to break it down into just simple series or parallel combinations. These more complicated networks need more sophisticated tools to sort of solve for the variables that we're looking for, and the tools that we need are supplied for us by this German physicist by the name of Gustav Robert Kirchhoff, who lived in the years you see here in the late 1800s, and he gave us the tools that we need to sort of address or at least solve for the variables that we want to in these systems. Okay, so his two rules can be broken down. Well, his rules can basically be broken down into two main rules. So there's Kirchhoff's junction rule and Kirchhoff's loop rule. Okay. So the junction rule tells us that the sum of any currents into any junction has to add up to be zero. Okay, so that's the first rule. We're going to talk about it more in a second. And the second rule is that the second rule being his loop rule, which is valid for any closed loop, is that the sum of the potential differences around any loop has to also equal zero. So let's take a look at these kind of really briefly here and try to get a feel for what they're saying. So Kirchhoff's junction rule sort of applies to any circuit where we have three or more conductors that meet, and really it would apply to points where two conductors meet, but that's basically just a line, right? You could draw a point on a line, and then we have a conductor coming into that point and going out of that point. And again, it has to be true that the currents have to sum to zero at that point, but that's kind of self-evident, right? So what Kirchhoff's junction rule is telling us is that the currents into any junction, if you add them all up, they have to be equal to zero. And this is kind of what we talked about in the last video and have been sort of alluding to. If we think of this water analogy, if we have water coming into a junction, let's say we have a river that splits into two streams, all the water coming down the river that splits into the two streams, if we add up the current coming in, it has to add up to the current going out. Otherwise, again, we have water pooling. This is the same idea as having charge pooling. We can't have that happen. So Kirchhoff's junction rule just tells us that we have to have the same amount of current going out as we had coming in to any point on our circuit here. So here we talk about specifically a point where we have three conductors meeting, but it could be any point. It could be 2 points or two conductors meeting basically in a sort of straight line, right? Kirchhoff's loop rule tells us that these jumps in potential difference around any loop have to sum to zero, and this kind of makes sort of intuitive sense if we think about it, because whatever potential we start at some point on our circuit diagram, if we go around a full loop and we end up back at that same point, we obviously have to be at the same potential. We can think about this if we think back to our discussions about potential, sort of in terms of a topographic map, right? You can imagine the circuit is just a path around some sort of a topographic map, and if you follow around any closed loop and you end up back at the same point on the topographic map, you're going to end up at the same point, which is at the same altitude, which corresponds to the same potential in our discussions about electric potential, right? So we have a couple of examples of what some of these more complicated diagrams might look like, and what loops and junctions are. So here we have a couple of more complicated circuits, and we can see that all the lettered areas are, well, okay, I mean, technically speaking, C and D here are not junctions, but the rule still applies. We have to have the same amount of current coming in and going out of each of these points. So really these are the formal junctions, A and B, and C and D aren't, but for all four of those points we have to have the same amount of current coming in and going out, and so Kirchhoff's junction rule would hold at all of these. And we can see that we have loops defined here for a number of different possible loops. You can draw a loop for any sort of loop inside our circuit. So here we have one big loop around the outside. That's one way we could think about current traveling around. We could draw another loop in here, another loop in here, or in this bridge diagram here. This is what's called a sort of bridge circuit. We're going to look at this more in detail as we do some examples. But we can see we can draw one big loop around the outside, then we have another loop in here, a third loop, a fourth loop, and you can draw as many of these loops, A, as you have loops in your circuit, or B, as you need to, because sometimes you won't need all the loops to solve for the variables that you're interested in, right? But we can see, sort of just going back to what we were talking about, Kirchhoff's loop rule, we can see in this diagram, let's say we start at point A, and let's say we follow loop 1. So we go from A across this R2 to C, across R4 to D, then over to E, then across our source here, so across the EMF, the internal resistance, to F, and then all the way back to A. Clearly we have to end up back at the same potential at A, because A has to always be at the same potential. We can't just keep going around and around the loop and getting more and more, or less and less potential at A, right? The potential has to be the same. So really Kirchhoff's second rule here, where any closed loop has to return us to the same potential, is somewhat intuitive, and so that's always kind of nice to work with. Okay. One last thing that we need to decide before we can use these rules, and we're going to do a number of examples if they're not, if it's not super clear sort of how to use this yet, but one thing we need to decide on before we do this is a sign convention for this loop rule. We're going to be going around the loop. We can choose any direction around the loop we want, but we have to choose a convention for the signs as we go over these different circuit elements. What sign are they going to pick up? Okay, so as we go over this thing, we're going to start at any point that we want. Okay. And we're going to go around the loop, adding up all the different EMFs and V equals IR contributions. So we're going to go around, and for example, let's say we were going across from F to E here or whatever, we would go across the resistor, we'd add that contribution, we'd go across the EMF, we'd add that contribution, and so on. We'd continue going around the loop. We want to make a closed loop, so if we were going around the loop this way, we would go across from F to E, then to D. There's nothing that we pick up there. From D to C, we pick up this contribution across R4, and then across R2 as we come up across here, and then back to F, if we were doing one in the opposite direction that's listed here. But we can choose any loop we want. We can do them in any direction that we want. We just have to follow this sign convention, okay? And so the sign convention that we're going to use is that when we go past an EMF source from negative to positive, this is going to give us a positive contribution. So when we go from negative to positive, we're going to pick up a positive contribution of that EMF, the value of that EMF with a positive sign. This is because we're going from low potential to high potential. So we can think of ourselves as going uphill in terms of potential, and so that term is going to be positive. When we go from positive to negative, let's say we go across the EMF in the other direction, this is going to give us a negative sign as we add that contribution, because we're going from high potential to low potential. Okay. Then when we go across any resistor, when we get these IR contributions, which are just the resistance times the current flowing through that resistance, if we're going through the resistor in the direction that we've assumed the current is flowing, we're going to pick up a negative contribution. Why is that? Because as we go across the resistor in the direction of the current, we're going from high potential to low potential. The current goes in the direction of decreasing potential, and so we pick up that negative sign. Okay, or if we go in the opposite direction, we pick up a positive sign because we're going upward in potential. Okay, and so this paragraph is kind of a mouthful here, but we're going to get used to using these rules, and it won't be as bad as we're doing some of these examples. So here we have sort of a quick little set of diagrams. that puts these rules into a sort of diagrammatic format that we can maybe more easily memorize. So we can see here that we get a positive contribution from our EMF if we travel from negative to positive. We get a negative contribution from our EMF if we travel from positive to negative. If we travel against the direction of our current from across a resistor here, we pick up a positive contribution, and if we travel in the direction of our current across a resistor, we pick up a negative contribution. Okay, and again, we're going to see how all this stuff works as we do examples here. I copied this directly from the textbook. I think this is from an older version of the text, but there's an updated version in edition 15 that you guys can look at. They're basically the same thing, and I really like the way the textbook kind of lays out their problem-solving strategy for this setup. So I'll kind of give it a quick look here. I would encourage you guys to give this a read-through so you kind of understand, and maybe pause the video or go back to it afterward and give it a read-through and really understand what they're trying to suggest as you go through each of these steps. It'll make it a lot easier as you actually work through each of these diagrams when you're trying to solve for variables. Okay, but basically the idea goes like this. You're going to draw the circuit diagram. You're going to draw it nice and large. You need to draw it large because you want to indicate on this diagram every assumed direction of our currents. Okay, so you're going to write down all the stuff that we know. We're going to write down the EMFs, we're going to write down the currents, we're going to write down the resistances. We're then going to assume the direction for these currents. Even if we guess wrong, it doesn't matter. If we guess the wrong direction for the current, we simply pick up a minus sign, and we know that our guess was the wrong direction and the current actually flows in the other direction. So that's totally fine. We go through, we label all the junctions that we're going to try to use Kirchhoff's junction rule on. We draw in all the loops that we might need to use. So for example, with these diagrams here, we're going to end up with 3 loops. We'll have the big outer loop, 1 inner loop, 2 inner loops. So we would draw in all those loops. And then we just choose whatever direction we want for the loops. It doesn't really matter, clockwise, counterclockwise. In the end, as long as we're using the same convention and adding things up carefully, it'll all work out in the end. So we have this big diagram. It has all the labels on it with everything we know and everything we want to know, all the variables that we need to look at, and then we simply start applying the rules. We're going to go through, apply as many copies of the loop rule and the junction rule as we need until we get enough equations involving the variables that we want to solve for, that we can solve for them. So if we have 3 unknowns, we need 3 equations to solve for 3 unknowns. If we have 4 unknowns, we need 4 equations to solve for 4 unknowns. Sometimes we're lucky, and we know enough stuff that these equations don't end up being coupled, and we can solve each equation on its own. Other times, there's too many things that we don't know. We need to generate a bunch of different equations, and we need to solve them all in a system to be able to extract the values that we need. We're going to see both of these examples in the problem set here that I'm going to be doing below. Okay, so give this another look. If after I've done these problems, it's not sort of clear how to do this, give this another look, and then go back and do some more problems to make sure that you do get a good feel for how this all works. Okay. So we're going to look at some examples like we usually do. I have the numbers worked out here next to me, so we'll take a look at some of these results, and let's see how we're going to do this. Okay, so the circuit shown below contains 2 batteries, each with an EMF and an internal resistance, and 2 resistors, right? So we see EMF with internal resistance, EMF with internal resistance, external resistance, external resistance. We have labeled 2 points on this this circuit, and this is sort of meant to look like a dead battery charging a live battery. Okay, and so we have this setup here. What do we want to find? We want to find the current in the circuit, so we want to find the current going around the circuit. We want to find what the potential difference VAB is, and we want to find the power output of the EMF of each of these batteries. Okay, and so how are we going to do this? Well, we're going to want to use Kirchhoff's rules here. We're going to start out by applying Kirchhoff's loop rule, and this should get us to being able to find what the current in this circuit is. So So let's say we started off, we wouldn't have these guesses for the direction of the current, and we wouldn't have this loop in here. But this purple and blue writing, this is stuff that we would put in ourselves, so we can guess, okay, maybe the current will be in this direction. Again, if we guess wrong, it doesn't matter. Our result will simply come out with a minus sign. It just means that the current actually flows in the other direction. We're going to choose a direction for our loop. Here they've chosen counterclockwise, so we'll do counterclockwise, but you could choose clockwise just as easily, or any direction you wanted. There is only one loop here, right? So there's only going to be one loop to look at. So let's apply Kirchhoff's loop rule here. We're going to start at point A here, and we're going to go counterclockwise around the loop, picking up all the contributions, and we're going to end up back at A here. And the loop rule is going to tell us that as we add up all the contributions from the EMFs and the IRs, the resistances times the currents, we're going to end up with 0, right? So Kirchhoff's loop rule, which we have up here is what we're going to be using, and it just tells us that the sum of all of these potential differences has to end up to be 0, right? And the potential difference terms are going to be EMFs and V equals IR terms, right? So let's go around the loop and see what we get here. Starting at A, I'm going to go around counterclockwise. So the first thing that I encounter is the internal resistance of this battery here. We're going to be traveling in the direction of the current that we've guessed, right? So we guessed this direction for the current. We're traveling in that direction. So since we're going across a resistor in the direction of the current that we've guessed, it's going to come in with a minus sign. So the first thing we get is minus I times the resistance itself, which is 4 ohms. We're then going to move across our EMF here. We're moving from positive to negative, right? So we're going downhill in a sense. So again, we're going to pick up a minus sign. This is going to be minus 4 volts. We then continue along the loop. We're going in the direction of the current across a resistor again. So we're going to pick up minus I times our resistance, 7 ohms. We're then going to continue up. We hit B. Nothing special happens at B. We continue along. We're going to go across the second EMF here of our live battery now. But now we're going from the negative to the positive terminal here. And so we're going to pick up a plus 12 volts. Okay. Then again, we're going across a resistor in the direction of our current. So we're going to pick up a minus I times 2 ohms. And finally, we're coming down this branch over here, and we're going to be again going over a resistor in the direction of our current flow. And so we're going to pick up another minus I times 3 ohms. Okay? And this, by Kirchhoff's loop rule, has to all add up to be 0. Okay? And so we can kind of clean this up, right? If I collect everything up, I'm going to collect up these two voltage terms here, and then I'm going to move all these negative IR terms over to the other side. If I do that, I'm going to end up with 8 volts is equal to I times 16 ohms. And if we clean this up and sort out the units, we're going to see that I has to be equal to 0.5 amps. Okay, so I is a half an amp. And it came in with a positive sign here, so that means our guess of the direction of the current flow was correct. We actually have a half an amp going around the loop like this. Okay, so that's an application of Kirchhoff's loop rule. In part B, we want to find what the potential difference from A to B is, right? So what VAB is. Excuse me. So let's try to find what VAB is. The way to do this, and they do mention this in the problem solving strategies, is that you can, here in point number 6 they mention it, you can use the loop rule to sort of go around the loop, but not fully around the loop, just from one point to another, and you can add up all those jumps in potential difference, and whichever direction you choose, you're going to end up finding that the whole thing is going to work out, and it's going to give you the potential difference between your starting and ending point. So let's do that. Let's take a look at this. I'm going to choose the bottom path here when I do this. So I'm going to travel from B to A, right? Because we're going VAB is going to be the difference between A and B. So we want to start at low potential and go to high potential. At least we're assuming that that's going to be the setup. So we're going to go from B to A. Let's take a look at sort of what we pick up here. So VAB, and this is again just one application of Kirchhoff's loop rule. VAB is going to be equal to, well, we're heading in this direction. Now we're heading against the current across a resistor. So instead of picking up a minus sign, it's going to be positive. We know that the current is now 0.5 amps. So we're going across this first resistor. We pick up 0.5 amps times 7 ohms. We're then going across our dead battery here, right? So we're going across this dead battery. We're going from the negative to the positive terminal. So we pick up a positive sign here. We're going to have plus 4 volts, okay? And then again, we're going opposite the direction of our current flow across another resistor again. So this will be positive, and we're going to pick up a 0.5 amps times our 4 ohm resistor, okay? If we add all that up, we get, what do we get here? We get 3.5, 4 more, and 2 more. So you're going to end up with a VAB equal to 9.5 volts, okay? So this is the potential difference between A and B. This is VAB, and we can see how we can use our Kirchhoff's loop rule to get this. We could have done the same thing going along this top branch here. We could have gone across the top battery and then down across this resistor. We would find the same result. Okay, and you can double check it if you'd like. Question C, what is question C? Question C, find the power output of the EMF of each battery. Okay, so we want the power output of the EMF of each battery. This is basically just a simple application of one formula that we know. So we know that P is equal to, well, we have 3 forms of this. So P is equal to VI, which is equal to I squared R, which is equal to V squared over R, right? And this is just basically this equation here, which is the definition of power, and we just use our definition V equals IR to sort of write it in a couple of different ways. In this case, we don't need any of these other different ways. We can just use this. Our V here is just going to be the potential difference across the EMF of the battery. And so the power output for our 12-volt battery is just going to be equal to the EMF of our 12-volt battery times the current flowing through it. And the power output of our 4-volt battery is just going to be the EMF of our 4-volt source, which is just going to be 4 volts, times the current again. The current is the same through the whole loop. We know it's a half an amp. And so this is pretty easy to calculate. We can get them both here in one shot. This will be 12 volts times 0.5 amps. Multiply that out, we get 6 watts. This one's going to be 4 volts times 0.5 amps. And so we're going to, but we have to be careful. I almost made a mistake there. We have to be careful because we're going in the current flow. Okay, so take a look at what's happening here in the current flow through the dead battery, right? We have current flowing in this direction, so we have current flowing from high to low potential, right? So because we have the current flowing in this direction, we're going from high to low potential, we actually have a negative potential across that battery. So this should have a minus sign. Careful with that. And so really what we have is a minus 2 watt power output. What does this mean? Well, this means that battery is draining 2 watts from the system as the current goes around, and that's exactly what we would want, right? We're trying to charge a dead battery in a car, right? And so it's draining power from the system. The 12-volt battery is supplying power to the system, and these are our 2 results, right? So these would be the two answers to the question, which was, what was it? It was find the power output of the EMF of each battery, right? So one of them is outputting power to the system, the other one is draining power from the system, okay? So that is one example. This is a fairly simple sort of application of Kirchhoff's loop rule here. We're going to see a more complicated one afterward, but I think we have something else before. Okay, that's a little more complicated. Okay, so what do we have going on here? So in this figure, we have a 12-volt power supply with an unknown internal resistance. So we have this setup here. Unknown internal resistance is connected to a rundown rechargeable battery with an unknown EMF. but we do know its internal resistance. So we have this set up here, unknown internal, we know the internal resistance, but unknown EMF here. And it is hooked up to an indicator light bulb that has a 3 ohm resistance. Okay, we see that here, and we have 2 amps going through this part of the loop. We have 1 amp going through this part of the loop, and we want to find, so we want to find what the current going through this part of the loop is. We want to find what this unknown internal resistance is, and we want to find what this unknown EMF of our rundown battery is. Okay, so we have 3 things we want to find. We want to find little r, the EMF, our unknown EMF, and that current in the section that we don't know. Okay, so in the end we're going to have to find sort of 3 equations to solve for these 3 unknowns. Here we're going to find that we're kind of lucky. Each of these equations is solvable on its own, so it's uncoupled. So we'll just find one equation, solve it, find another equation, solve it, find another equation, solve it in general. And as we're going to see in the next and final example that I'll be doing, they can be coupled, and it can be sort of much worse to solve. Okay, so let's take a look here to find. So let's just start off. We're going to use the junction rule at A here. We're looking for the current I here. And we can probably almost already see what it has to be just intuitively, right? We know that we have 2 amps coming in from here, and we have 1 amp coming in from here. So really we're going to have 3 amps coming around this loop. But let's see if that's actually the way that it works out. Let's use the junction rule. So junction rule at A. And so if we apply the junction rule, what do we have? Well, we have I going out, so we have minus I, that's our I going out. And we have plus 1 amp going in, that's this 1 amp here. And we have plus 2 amps going in from here, right? So we have 2 amps coming in from this left-hand side branch. Excuse me. And this has to be equal to 0. Okay? So I mean, I've included the amps here, but really what we end up having is minus I plus 1 plus 2 equals 0. I'm just going to mute my microphone to cough for a second here. Sorry about that. Okay, and so we can right away solve for this. Just move the I over to the other side. We end up with I equals 3 amps. Okay, and this is exactly what we thought we would find, right? Let's now take a look at the loop rule on loop 1 here. Okay, so this is our loop 1. We're going to take a look at the loop rule on loop 1. We're going to start at A, and the goal here is to try to find this resistance, this unknown resistance of our good battery here. Okay, so let's do that. We are going to start off. Maybe I'll scroll down a little bit. We're going to say loop rule start at A. And what are we doing here? We're going to go clockwise, right? So we're going to go 12. Yeah, okay. So we're going to go clockwise. Okay, so if we apply this rule now, we start off at A. Let's just start adding things up. So we're going to go along this from A down across our EMF. We're going from negative to positive, so we're going uphill here, which means we pick up a positive 12 volts. So we get plus 12 volts. Then we go across the resistor in the direction of I here, so we're going to pick up a minus. We're going to pick up a minus. Well, this is going to be 3 amps now. We know this is 3 amps from part A here, times our internal resistance that we don't know. We then go across B here. We're doing the outer loop, so we're going to want to go all the way down here, and we're going to go across in the direction of our assumed current here. So we're going to pick up a minus. It's going to be 2 amps times 3 ohms. Okay, and we know that this needs to be equal to 0 by the loop rule. Okay, so we can sort of clean this whole thing up. Again, I have all the units in here, but this really means that 12 minus 3r minus 6 equals 0. And we can kind of right away solve this. We just move the 12 and the 6 over, except we're going to pick up a minus sign there, so we can move the minus 3 over instead. So we'll end up with 6 equals 3r, which gives us an r equal to 2 ohms. Okay, so that's the internal resistance of this EMF source over here. Finally, we want to find the EMF of this unknown source here. So we're going to want to look at another loop to do that. We're going to look at the left-hand loop, so loop number 2 here, and we're just going to start at A and go around the loop. So we're going to start this way, go through B, and go around and pick up all the contributions. So let's take a look at that. Loop rule for loop 2. Start at A. Go, what do they go, clockwise? They go clockwise. Okay, so what do we get? We're going across the EMF. We're going from positive to negative, so we're going downhill here, and so we're going to pick up a minus the EMF. Then we're going across that internal resistor of 1 ohm, and we have 1 amp going in that direction, but we're going in the opposite direction of our current, right? So this is going to be a plus. So we're going to pick up plus 1 amp times 1 ohm. Then we are going with the direction of our current across this resistor. So we're going to pick up a minus sign. So it's minus 2 amps times 3 ohms. And this has to be equal to 0. Again, we can clean this up. This is going to be minus our EMF plus 1 minus 6 equals 0. And this just means that our EMF is equal to minus 5 volts. Okay. So notice again, like I mentioned, that none of our equations were coupled here, right? So we could solve each one on its own and get the variable that we wanted. Each equation only had one unknown in it. But it's possible that you end up with a more complicated system where you can't just go through, do one loop, get one answer, do another loop, get another answer. Sometimes you're going to have to get all the equations for all the loops and then solve them all together to be able to get to the answers. This is what we're going to look at in this next example, and it's a little bit longer here. The way the textbook does it actually is the way that I'm going to do it here, and it kind of shortens the problem. It could be worse than this also if you don't make sort of one of the logical leaps that they do here. Maybe we'll look at an example of this in class where we do it kind of a little bit more sort of without making the logical leap, so we have to actually do more calculation, but we get the same answer in the end. Okay. So what do we have here? This is the bridge circuit that we saw above, right? This is the same circuit that we saw in the very beginning up over here. Okay, so it's this bridge circuit B. We're going to be taking a look at it down here. What do we want to find? We want to find the current in each resistor and the equivalent resistance for the network. Before I get into this, I'm going to pause for a second and save this so we don't lose the PDF. Okay, so let's keep going here. I want to keep this on screen, but there's a lot to write, so you may want to like pull up a separate copy of this or write it down as we're doing this. So what are we going to do here? Now we can see that they've laid out 3 loops for us, and they've written in all these currents, but they were kind of clever about the way they did this, right? So they wrote out the 3 loops, and they said, okay, so coming out of C here, we're going to have I1 going this way and I2 going this way. We don't know what this I3 will be, but if we have I2 coming into A and we have I3 going out of A, well, it must be true that I1 minus I3 comes out of this branch here. Now this is going to make our calculation easier. This is going to mean that in the end we only really have 3 unknowns, I1, I2, and I3. But let's say we weren't that clever and we just ended up labeling each of these. Let's say we called this I1, called this I2, called this I3, call this I4, and call this I5. Could we still do this problem? We could, but we would need to generate more equations. So what we would end up needing to do is we would need to do this last loop that we're not going to have to do here, and we would have to apply the junction rule sort of manually instead of just making this leap where we're saying, okay, well, current is coming in, current is going out, so it must be the opposite going this way, right? So you could solve it, but they kind of take a more clever approach here. We'll use their approach here, and maybe in class time I'll look at another way to do this. So what do we have here? We have the loops that they're suggesting that we use, loop 1, loop 2, loop 3. They've labeled all of our currents. Take a second to sort of make sure that these make sense to you, right? So we have I1 coming in, we have I3 going out. So we must have I1 going out and I3 coming in here. So we have I1 going out in this direction, and so this minus I3 means that we would have an I3 going in, which is coming out, right? So that all works out at this junction here. Same idea over here. We have an I2 coming in and an I3 coming in, so we need an I2 and an I3 going out. And that's what we have here. I2 and I3 both go out here because I1 and I3 came in. Okay, and then so what do we have coming into D here? Well, we have I1 minus I3 coming in and I2 plus I3 coming in. So this minus I3 and this plus I3 end up canceling off, and we only really have an I1 plus I2 coming in. So we also have to have an I1 plus I2 going out. And that's what we have here. We have I1 plus I2 coming out of D and just going around the corner here, right? So all the currents kind of work out, and if you can make these sort of simplifications, it leads to a lot less equations that you have to solve. But we're going to see that even in this case, we still have to generate 3 equations in 3 unknowns and solve them. And it's not horrible, but it's going to take a little bit of algebra. And so let's sort of get into that now. Okay, so let's take a look at loop 1. Okay, so we're looking at loop 1. We're going to go around the loop. We're going to start off, let's start off at point D here. So we'll start off at point D. We're going to go around the loop like this, across our EMF, around, and we're doing loop 1. So we're going to go in through here, right? So this is loop 1. Let's add up all the terms. Okay, so we start off at D, we go this way, we go across the EMF. We're going from low to high, so we pick up a plus sign. It's going to be plus 13 volts. I'm going to bracket these off with the units. And then we're going to go into C here and across this 1 ohm resistor in the direction of I1. Because it's in the direction of I1, we pick up a minus sign, so it's minus I1 times 1 ohm resistor. That's terrible. There we go. Okay. So we've ended up here at A. Now we need to go across this other 1 ohm resistor. We're going again in the direction of the current, but our current now is a little more complicated. Our current has a couple of terms in it. That's fine. We pick up the minus sign still because we're going in the direction of that current. The current is called I1 minus I3 now, and we're going across a 1 ohm resistor. Okay, and that's that term. So we come out here, and now we've completed our loop. We're back at D. Okay, this has to be equal to 0. This is one equation. So one equation that we got from one loop. Okay, that one we're just going to call that equation 1. Equation 2 is going to be around loop 2. So loop 2 now takes us around the whole outside. Let's get that one going. I'm going to try to keep the diagram on screen while I generate these first equations, and then we'll work with them afterward. So what are we doing? Let's start at point C here, I guess, and we're going to go around loop 2. We're going to go across this 1 ohm resistor in the direction of I2. So we're going to pick up minus I2 times the 1 ohm resistor. Then we're going to go across this 2 ohm resistor in the direction of this current, which we now label I2 plus I3. So we go in the direction of the current, which means we pick up a minus sign, I2 plus I3, and this is times the 2 ohm resistor that we're going across. We go around this way, and again we're going across our EMF here, our source, from positive to negative here, so we're going uphill, so we pick up a positive 13 volts. Okay, this has to be equal to 0. This will be equation 2. So I'm going to do equation 3 here and loop 3 here in a second, but how do we know, how do we have any confidence that 3 loops will be enough? Well, each loop leads us to one equation, okay, and so we're going to end up with 3 equations. And we can see that we have 3 unknowns. So you're always going to need the same number of equations as unknowns, at least, if not more. And then you get into this whole linear algebra discussion about overdefined systems and so forth. But basically, you're going to want to end up with the same number of equations as unknowns, and then you can solve definitively for what each of those unknowns are. Okay. Let's now, I said I'd try to keep that on screen. Let's now take a look at loop number 3. So let's do loop number 3. We're going to start off at C, let's say, and we're going to go around loop number 3. So we're going to go across this this first resistor, second resistor, third resistor. Okay, and so for the first two, we're going in the direction of the current that we've assumed. So we're going to end up with a minus I1, 1 ohm, minus I3, again, 1 ohm, and then here we're going in the opposite direction of our assumed current flow, and so we pick up a plus I2, 1 ohm. Okay, this has to also be equal to 0. Okay, so 3 equations, 3 unknowns. We have a good chance at being able to solve this, right? So because I've written them down with all of these sort of units involved, I'm going to strip off all the units and just boil it down to some very simple sort of algebraic equations, right? So pulling out all the units, equation 1 is going to lead us to an equation that looks like this. We're going to end up with 13 minus I1 minus another I1 plus I3 equals 0, and we can rewrite that again. We'll end up with like a 2I1 equals 13 plus I3. Okay, so this I'm going to call equation A. If we look at equation 2, we can do a similar thing here, strip off the units, clean things up a little bit. We're going to end up with a minus I2 minus 2I2 minus 2I3 plus 13. Clean that up. 13 is going to be equal to 0, and again we can sort of rearrange this a little bit to get it a little bit nicer. 3I2 plus 2I3 equals 13. Okay, call that B. Now 3 can be used and cleaned up to give us, we're going to end up with, when I2 and the minus signs will go away. Okay, so we're going to end up with I2 equals I1 plus I3. Okay, that will be equation C. Okay, and now so we have these 3 equations. It's not immediately super obvious how we're going to solve for them, but really in the end you just have to substitute them into one another until you end up with a solution that you're looking for. So let's start off. This may not be the sort of cleanest way to do this. This is just a sort of brute force, start throwing things together and see how it works out kind of approach. So let's start off with C. I'm gonna solve C for, say, I1. I1 is going to be equal to I2 minus I3. Let's put this into A. If we put that into A, we're going to end up with, so we have A here. I'm going to jam the I1 in there. We're going to end up with 2 I2 minus I3 equals 13 plus I3. We can keep cleaning this up. We'll end up with a 2I2 minus 2I3 equals 13 plus I3. We can shift this around a little bit. Let's say 2I2 equals 13 plus 3I3. And let's solve this just for I2. So we'll have I2 is equal to 13 over 2 plus 3 over 2 I3. Now let's put this, and I'm going to run out of space here for sure. Let's now put this into B. Oops. No, that's supposed to be an into B. So if we put this into B, remember B looks like this here. So we have a 3I2 plus 2I3 equals 13. So we're going to have a 3I2 plus 2I3 equals 13. Now we have an equation just for I3. And I'm sure that there were cleaner ways to do this, but whatever. Let's just keep plowing on. So let's clean this up. We're going to multiply through by that 3. We're going to end up with 39 over 2 plus 9 over 2I3 plus 2I3 equals 13. And then we can collect up all these terms. we're going to end up with a 9 plus 4 over 2i3 equals 13 minus 39 over 2. We can clean this up further. We'll end up with a 13 over 2 I3 equals minus 13 over 2, right? 26 over 2, 13 over 2 is what's left. So if we divide through by 13 over 2, we're going to end up finding that I3 is equal to minus 1 amp. Okay, so what does that mean? Well, that means that the direction of I3 that we selected here is wrong, and it actually points in this direction, and it's 1 amp, and that's totally fine. We just leave it as minus 1 amp. That's our answer, and that just indicates that our current is actually pointing in the opposite direction. So that's great. We now have one of these. Can we go back and solve for the other ones? Well, yeah, for sure we can, right? That's the whole goal here. We take a look at equation A. Equation A is let's take a look at it here really quickly. Equation A, 2i1 equals 13 plus I3, so we can solve for that. So 2i1 equals 13 plus minus 1, and so this is going to end up giving us an I1 equal to 6 amps. Okay, so that is our I1. And finally, we want to find what our I2 is, right? That's the only one we don't have. Look at equation C here. Equation C is going to simply tell us that I2 is I1 plus I3. So I2 equals I1 plus I3. That's just going to be 5 amps. Okay. And so that gives us the 3 currents that we need. We can add combinations of these. So the problem asks us to find the current through each of these resistors. Well, we can just add up those combinations to get the currents through each of these resistors. We know what I1, I2, and I3 are, so we know what I1 minus I3 is and I2 plus I3 is. We can add those up, and you can give me all the resistances now, or all the currents through all those resistors, right? So we can add those up, and that's fine. The second part of the question asks us what the equivalent resistance is for this setup, right? And so we need to know what the current flow and the potential difference are, right? Because really what we want to do is we want to use maybe I'll do this. We want to use V equals IR here. We need to find R, so we're going to rearrange this to look like this. We know, well, basically we need V and I, but V is very easy to get. We can see that VA or VCD, I should say, the V across this whole thing, well, that's going to be the same as our EMF, right? Because this is just one chunk of conductor. So we know that our V is equal to our EMF, which is equal to 13 volts. So that's simple, right? So this is just going to be this. We need something in the basement here that I haven't included, and this is just going to be 13 volts, right? But what is our current around the loop? Well, because of the simplification that we made, we can see that the current coming through here is just I1 plus I2, right? And that means that I1 plus I2 has to be what's coming into here, and we can see that that's the case, because coming out of C we have I1 plus I2, so coming in must also be I1 plus I2. So the current flowing around the outer part of this loop, and if we imagine this as a single resistor here, the current flowing through that single resistance would be I1 plus I2. Okay, so what is I1 plus I2? Well, I1 is 5 amps, or 6 amps, and I2 is 5 amps, so adding those two up gives us 11 amps. So we end up with well, I guess I'll write it I1 plus I2, and this is 11 amps. And if we do that division, we end up with an REQ equal to 1.2 ohms. Okay, so that's the equivalent resistance of the setup that we see here. Okay, and that's the answer to that problem. So there are other examples in the text that you guys can look at. Some of them are pretty good. There's a lot of examples at the back of the text. We'll look at some in the assignment, and I'll probably do one similar to this at our weekly meeting here. But this is basically Kirchhoff's rules and how we apply them to systems that are a little more complicated than just straight up series and parallel resistors. Okay, so I'll leave it here for this one, and I'll see you guys in the next one.